Thank you, Mrs. Berg. Good morning, everybody. Hope you've had a good week so far. Thanks as always for your flexibility and goodwill. Last Thursday, we learned from Dr. Nahid Bhadelia about viruses, what they are, how they behave, and how COVID-19 in particular has developed into a global pandemic. This morning, for our part two of sorts, we welcome Dr. Galit Alter, who will help us better understand how we collectively might emerge from this situation. Dr. Alter is a professor of medicine at Harvard Medical School and a group leader at the Ragon Institute of MGH, MIT, and Harvard. Her work focuses on the development of biological tools that help individuals develop immunity against infectious diseases. As Dr. Alter has described in some of her writing, it was in the early 18th century that the practice of inoculation or vaccination emerged, when the development of the first vaccine burgeoned into the field of vaccinology. Despite many advances in our understanding of the immune system, antibodies, and our ability to make vaccines, vaccinology still relies on mimicking a pathogen to induce immunity, a practice which continues to fail in many cases. Dr. Alter and her colleagues aim to change vaccine design to generate more effective vaccines and drugs, quote, closing the gap in our understanding of how we resist infections and malignant diseases, end quote. We have heard much recently in the news about the global rush to develop an effective and safe vaccine against COVID-19 in order to save lives, resuscitate our economy, and allow us to return to the routines we enjoyed pre-pandemic. This morning, Dr. Alter will help us understand the scientific process necessary for that reality and enlighten us essentially to what we might expect in the months ahead. Dr. Alter earned her bachelor's degree and PhD at McGill University and completed postdoctoral training in the Partners AIDS Research Center at Massachusetts General Hospital. She is a two-time recipient of the prestigious MGH Research Scholars Award and was elected a member of the American Association of Microbiology in 2019. I hope you'll join me in welcoming to Roxbury Latin this morning, Dr. Galit Alter.
Thank you, Mr. Brennan. And so good morning to everyone, and thanks for the invitation. I thought that I would give you all kind of a fun morning introduction to vaccinology, and then to leave off the conversation with a couple tidbits of hope about the path for the development of a vaccine against SARS-CoV-2, the virus that causes COVID-19. So I'm just going to project my slides. Give me a second, and let me know if you can see the screen. And so what I'm going to do is I'm going to take you on a little bit of a historical journey to the beginning of where vaccines began, and to give you an idea of how vaccines work, and then move into what's happening in the coronavirus design space. So the concept of vaccination, I love looking at a lot of really interesting sources of information, and I still think that one of the best sources of information that we have is Wikipedia. And so if we just look at the definition of a vaccine, they are spot on. The idea of vaccination is really simple, and it is literally taking a substance, and that substance can come in lots of different shapes and sizes and qualities. And you take that substance and you put it into the human body, and you ask it to make antibodies or an immune response. And we hope that through this process, we educate the system, the immune system, to essentially fight a pathogen should we ever come in contact with that pathogen in the future. So this is the whole concept of vaccination, is taking something, figuring out what that something is really the important part of the educational process, and then understanding how it induces those responses and making sure that they are protective and that they last. Those responses last for a really long time. Now, vaccines, although they get some bad press sometimes, and we've heard some really interesting dialogues, I think, in the media over the last few months, vaccines save millions of lives every year. The estimates put us at 2.5 million children's lives that we save every year. That's the entire population of California that we save every year because we have vaccines. Vaccines are literally one of the most effective public health tools that we have in the medical toolkit. They provide protection, which often is intangible. We can't understand it in the public domain, but I'm just going to explain to you how they work and what the efforts are around developing one of these types of vaccines for this particular pandemic. Now, the reason that there's all this bad press, and I really love to start my talks with this little concept, is that there is this murmuring or this little chatter in the background in the public domain that relates to this one story. So I don't know if you guys have all heard this, but once upon a time, there was a study that was published in a highly reputable journal called The Lancet. It is one of the most reputable journals we have in the scientific community. And in this journal, there was a conclusion that was drawn in a paper that suggested that vaccines caused autism. The study was incredibly erroneous. There were all kinds of problems with the study. And somehow, like in all communities, things sometimes just slip through the cracks. And this paper got published. And the idea that they put out there in 1998 was really a myth that essentially kids who got a vaccine, it was the measles, mumps, and rubella vaccine, MMR, somehow became more apathetic after they were vaccinated. It was a qualitative study. It was all done by interviews over the phone. And unfortunately, because the study was not designed correctly and because the data was not interpreted in a statistically robust way, this led to a conclusion that basically led the public domain to start believing that this was a real association between vaccination and autism. What happened after the study was published is the vaccine field and the entire immunology and medical field raised their hands in uproar. And what they did is they systematically dissected all the problems with the study. And there were thousands and thousands of responses to this paper that were published on the Lancet website, showing all the reasons why that study and those conclusions were absolutely wrong. In response to that, the authors of the manuscript were forced to retract their paper. Retraction is probably one of the most horrible things that can happen in the scientific community. It essentially means that everything you did in that study was wrong and you admit it. Now that study was retracted and hundreds of studies have taken place since then and have clearly demonstrated that there is no linkage between autism and vaccination. There are still many, many questions about what it is that does potentially trigger autism or forms of Asperger's disease. And those studies are underway, and we are making incredible headway in understanding those biological cues and those biological processes. But the one thing that is certain is that the association identified in this study was absolutely wrong. Despite that, this is what happens. You get these cartoons that are actually real. And somehow there are some movie actors and people out there in the public domain that refuse to listen to science. But I can tell you one thing, science is hard facts. And when the hard facts do not show that there's an association, then there is no reason to believe that little statement out there in the world is really real. So what are the myths with vaccines? Well, one myth is that vaccines are only for kids. That is not true. Adults get vaccines all the time, and I hope you're all going to go out and get your flu shot, because even though we're wearing masks, it may be a bad flu season this year. Adults also get vaccines when they travel around the world, and it's really important when you go to foreign countries, hopefully when travel restarts again, is to go and make sure with your travel clinic that you are immunized against the pathogens in the new locations you're going to visit. Vaccines vaccine preventable diseases outbreaks don't occur anymore. As we know, that is not true. Measles does come back once in a while, and it causes really incredible disease spread. So it's really important that we keep vaccinating populations over time and don't become complacent about the vaccines that we deploy across the population. There's a myth that vaccines are not safe. That is absolutely not true. We are incredibly vigilant. We are monitoring every single experimental vaccine as well as established clinical vaccine, always making sure that we are monitoring and aware of any kind of potential adverse events so we can rectify those situations and make safer products that can go into individuals across the ages. Prevention is out of my control. That is absolutely not true. Getting your vaccine in time will certainly help to control and prevent diseases, and you can't get vaccinations while pregnant. This is not true. Tell all your friends and family. Vaccines during pregnancy is really critical for helping itty-bitty babies before they are born. So how do vaccines work? And I just want to make this point because I think this is a really important idea and concept out in the vaccine field. Vaccines are not only for you as an individual, but they are something we do for our community. We do this for our friends, our families, our neighbors, our country, and our globe. We take the responsibility to prevent infections from hurting those that are most vulnerable. So this is a beautiful image and explains how vaccines work. So in the in the potential scenario here on the left side, where only some individuals get vaccinated. Here we have the healthy individuals that are not vaccinated in the blue. So these are people who are potentially susceptible to an infection. The individuals in the yellow are the individuals who get vaccinated. So these are the individuals who are theoretically safe or protected from a vaccine. And if we have one individual here in the middle who is infected with a virus, like the coronavirus that's out there right now in the world, if you have a lot of people who are susceptible, the virus can propagate very quickly because there's very little protection in the population. And so what happens is when you have very low vaccine coverage, if only 10, 20, or 30% of people get vaccinated, then the virus will keep spreading, and it will spread like crazy as fast as possible. Now, imagine a world where now, instead of only covering 20, 30, 40% of our population, let's say we can cover 80 to 90% of our population. Let's imagine a world where we can deploy the vaccine instantaneously to everybody who's willing to take it. Then you have very few susceptible people. You essentially build a wall around the virus. And what happens when you vaccinate these individuals, even if one individual once in a while becomes infected and becomes a potential spreader, that virus cannot get far. It is really walled off from those individuals who might be most vulnerable. And maybe we'll get one infection in 100 or 1,000, but we certainly will not see the devastation that this particular virus is causing today. So it's our responsibility to create this wall around the virus and to make sure we protect those individuals who cannot get vaccinated or those who are not able to respond to the vaccine quite effectively. So we're protecting the young and the very old. Now, I just want to take a little step back. As Mr. Brennan mentioned, is this idea of where vaccines came from. So the idea of taking a substance and putting it in someone, this is not a modern concept. This has been around for hundreds of years. Now, probably the most famous case that you all heard about is from a doctor named Edward Jenner, who back in the late 1760s, really around 1765, he performed a crazy experiment. And it was an experiment that was not completely unfounded, but at the time it was, a little bit controversial whether this was going to work. So what Dr. Jenner had noticed was really something quite interesting. What he noticed was that in the big cities in England, there were a lot of kids who were getting infected with smallpox. It's a devastating disease. If you ever have a chance and you have, and you're not too scared by scary images, take a look at what smallpox looked like, because it was a devastating disease that killed thousands upon millions of kids back in the 18th century. Now, what Dr. Jenner had recognized was that in the big cities, there were lots of kids that were getting infected with smallpox. And at the end, they would all have these scars from this pustules that would form all over their skin and their body. And he noticed that if he looked into the countryside and rural communities, he noticed that there was a population of young people that never had scars on their faces. They were never clearly infected or exposed to the virus, is what he thought. These were all milkmaids. They were young women that had beautiful milky skin. These were the women that worked to basically collect the milk every morning from the cows. So he asked himself, why are these milkmaids, why are these young women protected from this virus that is so lethal and so infectious in the general population in the cities? And what he got to realize is that actually it's not just humans that are affected by smallpox, but cows can also get a disease which is very similar called cowpox. And the hypothesis that he developed was really quite simple. And that was that potentially, because these women are exposed to cowpox, they might make an immune response to this pox virus that might protect them from smallpox. So what Jenner did was he decided that he would take a little bit of the juice from one of the cowpox pustules. He put it into a syringe-like device, and he injected it into the arm of a young boy who was one of the milkmaid's sons. And he waited and saw whether this boy would develop smallpox. And lo and behold, this little boy was completely protected upon exposure to other kids with smallpox, never developed pustules. And this was really the first scientific identification or observation of protection from infection from smallpox. Dr. Jenner went on and did multiple trials proving the concept was real, both in kids as well as in adults in prison situations, where he then immunized hundreds upon hundreds of individuals, proving to the Queen of England that this approach of essentially taking the pustule and putting it into a person's arm could raise immunity against this devastating lethal pathogen. This gave rise to the concept of vaccination. But he wasn't alone, because soon after, almost in parallel, there were others that came along that began to revolutionize our capacity to start making vaccines. Another incredibly famous individual named Dr. Pasteur, Professor Pasteur, who many of you may have heard of, really took vaccines to a whole new level. Now, the interesting fun fact about Pasteur was that he was not a vaccinologist, nor was he a physician. He was actually a chemist. And what he was hired by the emperor or the royalty in France was to develop strategies to pasteurize or essentially clean food of pathogens, and essentially to develop the whole viniculture or wine industry is what his job was. In the process of learning how he could essentially disinfect milk and liquids and fluids and wine of pathogens, he began to realize that he could actually sterilize a whole lot of things. And in the process of sterilizing different pathogens or sterilizing different kinds of fluids, he realized that he could take a pathogen, he could essentially kill it in a process, in a chemical or heated process, and then he could take that killed pathogen and put it into an animal and protect it from infection. So this was a whole idea that Pasteur came up with that completely changed our ability to develop vaccines, where he could now take bacteria and he could essentially put those killed bacteria into animals and protect them from infection, whereas the animals that did not receive the pathogen, this killed pathogen, would essentially die. So he created this whole field, essentially revolutionized the whole field of essentially taking any pathogen you can imagine, killing it. You can still have all the components of the pathogen there. You can take those components, put them into the arm of an individual, and you could drive the induction of antibodies. So this whole process was really the inception of a chemist who was essentially hired to develop wine. He came up with a whole field of heat-killed vaccines. Soon afterwards, Koch from Germany came up with an important postulate that advanced how Pasteur began to develop vaccines. And interestingly enough, if you ever have a chance, you can go back in history on the internet and take a look. Koch and Pasteur really hated each other. They would fight like there was no tomorrow at scientific symposia, because Koch really challenged Pasteur and made Pasteur realize that it's not that it's just any pathogen you can put into a person that will raise the right immune response, but you essentially need to come up with a set of rules that allow you to identify the right pathogen that is causing a disease and develop strategies to prove that that pathogen and the method that you use to kill that pathogen is still intact enough that it can essentially still drive an immune response. So Koch essentially created the path of pathogen identification, pathogen attenuation, and proof that the pathogen can induce the immune response, really giving rise to the checkpoints that we use in the vaccine development program. So his postulate was really key, and the postulate says that you have to be able to identify or isolate the pathogen from an infected animal. And that pathogen you must be able to grow it or isolate it. You have to be able to then take that pathogen and put it into a healthy mouse and prove that it actually causes disease. Those checkpoints and that verification was absolutely essential, and basically made sure that in the domain of vaccine development, that we weren't immunizing people or putting products of pathogens into people that were not lethal or that could cause adverse reactions. So this was really the tenet that Koch positioned to basically create checkpoints and safety within the vaccine development pipeline. Now, what's interesting about vaccine development history is that it was not Jenner, Pasteur, and Koch who really invented vaccines, but there is evidence, if we go all the way back to ancient China or ancient Greece or ancient Egypt, there are examples in drawings and lithography and hieroglyphics of individuals performing the art of vaccination. So this is a really interesting ancient Chinese diagram that is still used in medical literatures that shows an example of an individual who probably had smallpox. These are these little pustules that I mentioned before all over their body. And the idea was that one could essentially take the liquid from those pustules, and then you could essentially use them to inoculate and immunize another individual. The same is true over here in this ancient Greek vase. This is an example, again, of someone who is being immunized against a pathogen. And there are many examples of this, where the art of vaccination probably existed hundreds of years before Christ. So what we learned from ancient Greece was this awareness that one could induce immunity. We are not completely vulnerable against pathogens, but we can arm ourselves and we can arm our immune systems with knowledge of a pathogen before it infects us that can drive the induction of protective responses that can allow us to resist those pathogens. Jenner then modernized the whole concept of vaccination by essentially coming up with strategies in a scientific way that he could show exactly that taking material from one particular pathogen and putting it into a human could potentially give rise to this immunity or this natural response to the pathogen. Pasteur then took it to the next level, where he realized that we could do this for almost any pathogen. We don't have to find it in cows or horses or mice. We can essentially identify a pathogen, we can attenuate it, or we can essentially kill it through heat or other chemical processes, and use those itty bitty pieces to do what that definition in Wikipedia said, is to take the material, put it in the body, and drive an immune response. And then it was finally Koch who helped us understand how we could identify that pathogen and make sure that the pathogen and components we use are truly safe and effective in driving protective immune responses. Now, since the 18th century, vaccine development has exploded. We have hundreds of different approaches, technologies, and platforms that allow us to essentially drive immune responses. What we've come to appreciate since the time of Pasteur is that we can use more than just the whole pathogen or the heat-killed components of the pathogen, but we can deliver components of our pathogens in lots of different ways. We can attenuate the way that Pasteur did it. We can deliver it through DNA or RNA, which essentially allows our body to make those components through our own cells. It's a really interesting and very fast way of developing these tools. We can also use other kinds of chemical processes to make these components of a pathogen in a way that our immune system can see them more effectively. And probably one of the most modern and interesting ways that we have learned to drive immunity, other than making the components ourselves through chemical synthesis of proteins or carbohydrates that decorate pathogens, is the use of other carrier viruses. So viruses that we deal with every day, they don't cause any disease or any infection, and we can use those viruses to essentially deliver these components of the target disease-causing pathogen to the immune system, taking advantage of the fact that viruses that don't really cause disease in us can still get all kinds of material into the immune system and can help the immune system see those components and potentially raise more effective immune responses against them. So of the vaccines that are out there to date for the SARS coronavirus, there are a number of examples of whole pathogens that are being used coming out of China, some really exciting attenuated SARS-CoV-2 viruses that are being explored, and data are gonna be released very soon on the efficacy of this platform. There are also the AstraZeneca vaccine and the J&J vaccine that both take advantage of these innocuous viruses that we use to essentially deliver material to the immune system. And then what we've learned from Pfizer and Moderna and a few others is the use of RNA becomes a really simple and fast platform to essentially give material, or essentially the code to express the SARS-CoV-2 antigen in our own cells to program the immune system to essentially drive immunological immune responses. But the vaccine development pipeline really takes a whole lot of time. And so where in the days of Jenner and Pasteur and Koch, they would identify a virus, they would essentially attenuate it and potentially inject it in someone's arm, these days, making a vaccine really does take an awful lot of time. There are years upon years of time that is spent in academic labs, at the basic research bench, really trying to understand what is the pathogen, what components of the pathogen are the most important components that we want to drive immunity against. This is really the discovery component of vaccine development, and this sometimes can take upwards of a decade. Once we identify the components that we are most excited about, as well as the platforms that we want to use to deliver those components, we then spend years trying to prove to ourselves in animal models that those vaccines do provide protection in the same way that Koch told us back in the 18th century that we had to prove to ourselves that those vaccines work. And then once we hit those milestones and we're able to show ourselves that that actually works, we then move into clinical development. And this is where we have a staged process of going through safety and efficacy testing, I'm going to show you in just a minute, that allows us to essentially hit all of the regulatory checkpoints that show us that what we're putting into an otherwise healthy human is actually safe and effective. So this process normally takes at least 20 years, and that is the typical vaccine development timeline. So this is really what it looks like if you stage it out. So you have here the development component. This is the typical vaccine timeline. You have the preclinical phase. If you pass that, if you are successful, you can move to phase 1, where you're testing to see whether a vaccine is safe. You put it into a small number of volunteers, and you make sure they're not developing any kind of autoimmune disease or any kind of strange symptoms. This happens very, very rarely, but we are very safe, and we make sure this doesn't happen. Once we finish the phase 1, we go into phase 2. And in phase 2, this is where we ask a larger number of volunteers to allow us to look at the immune response and to see, is it strong enough? We're not asking if they're protected. We're just asking, is the vaccine giving us the quality and the functions that we think are going to be protective against the virus or the bacteria or parasite based on what we had seen originally in our preclinical animal models? And once we pass that checkpoint, we move into phase 3. Here's where we look to see in a very large population, tens of thousands of individuals sometimes, whether the vaccine is protective. And if that works, then we move into building factories, making billions of doses, manufacturing. We get FDA approval. The FDA has to check to make sure that this lot is actually as good as the original lot. And then we can move into distribution, which again can take years. So let's say we started this process in 2020 when the virus hit. It would take us till 2036 to be able to complete the entire timeline if we went by the typical vaccine process. This is what happened for coronavirus. The world changed. Everyone started thinking, how do we overlap activities? How do we still do this in a safe and effective way? And hopefully what you can see here is a timeline that would have otherwise taken 16 years was condensed into less than 2. And the reason we can do this, and I just want to stress this really important point, none of the components are gone. They are all there. All the safety checks, all the quality checks, all the efficacy checks are still part of this process. We have not gotten rid or skirted any component of this entire process. What we've done is we've just created overlapping ways of basically running this entire timeline so that we can get to the vaccine faster and get it out to people as quick as possible. But this will also give you an idea of when to expect the vaccine will roll out for this particular community. So we skipped academic research. We essentially took the virus sequence that we got back in December, and we inserted it into already established vaccine pipelines. So each of the vaccines that are now in clinical trials have already been vetted through other types of infectious disease indications. And we know that the J&J platform is safe. We know that the Pfizer platform is safe. We know that the AstraZeneca platform is safe. But now what we're doing is we're running the preclinical trials with the phase 1s together in tandem, as you can see here. They're running at the same time so they can inform each other. And we're making sure that the insertion of the SARS-CoV-2 protein or component is giving us the right immune responses, that we're not seeing any potential adverse events. Now, with that data in mind, we can then begin very quickly the phase 2, which obviously happened for some of these vaccines. And if the immune responses look effective, and I'll show you some of those responses, which look great for these particular vaccines, then we can move directly into phase 3. And the phase 3 timelines are shortened. And we are fortunate that we can do this in the context of this particular epidemic, which allows us then to get approvals happening right away at the start of 2021 or mid-2021. Now, importantly, the big deal activity that happened that completely changed the game for us is the fact that the government, as well as these major vaccine developers, began to take risks that they had never taken before. And what I mean by a risk is that vaccine developers typically will not start making, building factories and building the vaccines and making billions of doses before they know that a product will work. They won't take that financial risk because that's basically, gambling, right? You don't know it's going to work and you're still going to basically invest hundreds of millions upon billions of dollars to make a product that you may not know will actually go out in the population. But because there was such a need, because the vaccine community got together, that basically created the incentive for them to begin to build factories even before they had the data and knew whether or not the phase 3 trials were actually going to show efficacy. So that was a huge game changer. And now we'll have the products will be ready in time. They'll be ready by the end of the year, essentially. And they will then allow us to basically, as soon as we get approvals from the FDA and other regulatory bodies, to begin distribution in mid to late 2021. So think about that as a timeline for when vaccines will start to roll out. So how do vaccines work? I just want to go through a little bit of the immunology because I think it's important to understand what we're putting into our bodies. So again, it's a substance we put into the arm or a part of the body, and we hope that the immune system will grab it and then will essentially learn how to make a response. The concept of vaccination essentially is very simple. It is teaching the immune system to fight an infection. So vaccines basically allow the immune system to generate the right kinds of responses. It arms the immune system, and more importantly, it helps to direct the immune system very effectively and very aggressively against a pathogen should it enter our body. Now, one key point about vaccination is that one shot is often not enough. And the reason for that is just like, school every day. We never learn how to do a math problem once, but we repeat it over and over again. So it kind of sinks into our memory. Well, the same thing is true for vaccination. We need the immune system to not only see it once, but we want it to practice. And so by giving a shot a second time, which may be the case for this particular virus, we're going to have to do probably 2 rounds of immunization. The reason we do that is to get the immune system kind of practicing to make sure that it can really burst if the virus comes along. So how does it work? So let's look over here on the left side. Here is the vaccine, and it's got some products in here, some parts of our pathogen or the components that will induce the immune response. We inject that usually into the arm, but in some cases it might be a little bit different. For some vaccines, we deliver it into the skin, and for others, we even inhale it. But for the typical vaccines that we are seeing now for SARS-CoV-2, they're going to get injected into the muscle. Once it gets injected, these components here, these little red stars, go into the tissue in between our muscle cells, where there are immune cells called dendritic cells. These are really special sentinel cells that recognize when something foreign comes along. These cells are kind of the master educators. Let's call them, the Mr. Brennans of the immune system. And what they're there for is they're checking to make sure that everyone's in class and everyone's doing their job. But once in a while, he might notice that there's something going on. And what these little guys will do, these dendritic cells, is they'll pick up these components of the virus. And what those cells will then do is they will bring them over to the immune cells that can then learn and teach all of the students in the immune system to essentially begin to recognize this foreign material as something that they have to recognize and attack. So what happens is these dendritic cells will pick up these components and they will move essentially to a different organ, which is an immune organ called a secondary lymphoid tissue. Let's think of this as a little classroom. He brings it over to where we know all the cells that need to be educated live and they traffic. And what that dendritic cell will do is it'll start to present these components to the little students, all these naive T cells and B cells that circulate in our body. And we'll start to teach them to recognize these particular components and essentially go through the process, an iterative process of essentially teaching and reteaching over and over again until these cells can essentially leave these organs and start to circulate and make sure they populate the blood with lots of cells that can kill this pathogen. So this is just an example of this process. You pick it up, you bring it to the classroom, and they can then leave and they can populate the immune system. And some of these cells will even go into the bone marrow where they will drive long-lived immunity. They'll live there for their entire lives. And in that tissue, they will continue to make antibodies your entire life against this pathogen. So you'll have protection forever against that particular foreign material. So as I mentioned before, we don't do this just once. Teaching does not always work if you give it just once. With some vaccines that, will keep this teaching process going for a long time, you might get away with a single shot. Some of the vaccines for coronavirus seem to be doing an okay job. But what's interesting is that we seem to need a second round of immunization, the second boost. So we have the primary response, the secondary response. This secondary antigen challenge is really what helps the immune system really get it. It helps the message sink in, and it helps the students really remember that this is what they have to attack, and they have to attack it in a very specific way. So one of the key components of these immune response is once these cells learn how to make a response to the pathogen, what these cells will end up doing is they will help B cells make antibodies. And so antibodies are really what we believe is the key mechanism of protection, or the key to protection against almost all pathogens. These antibodies recognize pathogens, and making these antibodies and having them around for life is really critical for long-term protection from infection. So how do antibodies work? So the idea in the vaccinology field is that if you can drop a vaccine into someone's tissue and they can get to the classroom and teach the cells how to make just the right antibodies that can essentially see the virus in just the right way, that those antibodies will block the virus and prevent it from ever being able to get into a cell. These are called neutralizing antibodies. And this is the dogma in the vaccine field, is that if we can get vaccines to induce these kinds of responses, then we will have protection from infection. And for most pathogens, these kinds of vaccines is all you need to essentially achieve protective immunity. And interestingly, for SARS coronavirus, that seems to also be the case. Having antibodies that can neutralize the pathogen is the correlate of protection from infection. Now, antibodies do a whole lot more, and I just want to give you a little tidbit of fun facts about antibodies, because it's not that they only block infection. But let's use an example here of a virus. It gets into a tissue. In the context of coronavirus, it's coming through the nose, and it's infecting cells up here as well as going down to the respiratory tract where it infects additional cells. So let's say it gets into a tissue. And once that virus gets in, that virus will infect a cell. Once it infects, it'll infect a few more cells. What is happening is that the virus starts to spread really effectively. So we think in vaccinology that if we can make a vaccine that could essentially block that first stage, really prevent those first infections from happening, those are going to be the key, most critically important antibodies that will provide protection from infection. But once in a while, a virus will slip through. And so what we want is we want backup mechanisms. We want to have additional strategies to make sure that those little viruses that might escape into an infected cell will not essentially leave us vulnerable to potential disease. And so what it turns out is that antibodies do something different. They don't just recognize the virus, but they can recognize the first infected cells. And what's amazing about antibodies is that they actually have two ends. They are Y-shaped molecules where the tippy tops of the antibody are involved in recognizing a pathogen, and the bottom of the antibody is actually involved in recruiting killer cells from within the body to essentially destroy and kill all the viruses and the infected cells. So these are the kinds of mechanisms that we are most excited about. So this is the last slide. Is that okay, Erin? Okay. So this is, do the vaccines work? So there are two ways we can ask that. Do they respond? Do humans respond to the vaccine? As well as can we put them into animal models and ask, do they respond? But more importantly, are they protected? So here is the data about protection, just to give you a little grain or a little bit of excitement, is that when these vaccines, and I'm just showing you three here, the Moderna vaccine, which is an RNA vaccine, AstraZeneca, which is one of these innocuous viral particle inducing vaccines, and the Janssen vaccine, which again is a viral particle inducing vaccine. Hopefully what you can see here is that here are the control animals. When they are challenged with the virus, they all get infected and get lots of virus. This is virus here on the y-axis. But in the vaccinated animals, there is zero virus inside the tissues of these animals. And the same is true here with the RNA vaccine from Moderna. There's no virus anywhere in these animals once they're challenged. And the same thing is true here for the AstraZeneca and the red dots compared to the blues that are the control animals that did not get the vaccine. The red dots are always completely clear. So they all work, at least in animal models. So I just want to leave you this last thought, that there is light at the end of the tunnel. You guys are all going to get out of your houses. You're not going to have to wear those masks for the rest of your lives, at least not for coronavirus, maybe for other pathogens, and maybe for pollution, but who knows? But I think that the important point is that this is not the first or last virus that's going to enter humans. This is not the last one that's going to jump. And so we need better, cleverer ways to make these vaccines. And so we need all of you guys to commit to being part of making the solution happen. So, think about immunology and vaccine development as a future for your careers. That's it.
Dr. Alter, thank you so much. That was a masterclass on a Thursday morning. So thank you so much for being with us. We do have a couple questions, and I told you last week we didn't get to questions, so I promised we would get to them today. So we have a couple that have come in, and I'm just going to start off at the top here. The question: what makes chicken eggs a good choice for growing vaccines, and specifically flu vaccines? Because we hear often that people that are allergic to eggs should, have a concern about the vaccine or something.
Yeah, so this is like a really archaic way of how we made vaccines, but it hasn't gone away. So what happens is that flu grows incredibly well in chicken cells. It's a really interesting thing. So I don't know if you guys have heard, but flu comes from two animal sources. In nature, it comes from pigs and as well as from fowl, from birds. And so we have bird flu and we have swine flu. But what's interesting is that all flus seem to replicate incredibly well in bird cells. And so eggs are a really easy source of lots of cells, right, from birds. And they're a really nice way that you can create like little mini incubators. And so what we can do is you can inject virus into an egg. You just have to put 1 or 2 particles in there, and they essentially replicate and they copy themselves billions and billions of times over in eggs. That gives us a little tiny little mini factories for making vaccines. And so this really was like the first way that Sanofi Pasteur, one of like the biggest flu vaccine companies, started to make vaccines for flu back in like the early 1900s. And that technology has not gone away because it is such an efficient way for making flu virus that we then collect from the eggs, and just like Pasteur had done it, we break it into pieces with heat and other processes, and then we use those components then to basically make itty-bitty vaccine vials that then go into people's arms. So the reason we tell people who have egg allergies not to take the flu vaccine or that flu vaccine is because it is made in chicken eggs, because they are just really the virus really likes to replicate in them. There are newer technologies now that are being explored though. There are essentially lab-based technologies that can basically just replicate like a kind of protein photocopier. We can make the proteins ourselves now in a synthetic way in the lab. And that's going to probably at some point replace the chicken process because it is much more efficient, much cheaper, much cleaner. But for now, we tend not to change the vaccine development pipeline completely until we are absolutely sure that we have something that will band-aid and completely replace it in a safe and as effective way.
Thank you. Next question is, if a vaccine is anticipated to be approved possibly by the beginning of next year, how do we know that the immunity conferred by the vaccine is durable?
Well, that's a tough one. So that you only know by following individuals over time. And so we will, for many of the trials that are ongoing now, the phase 2 trials, they are following people for longer periods of time. And so we will see what the data look like, and we will probably know by then whether we're going to need 2 shots, maybe we're going to need a 3rd shot to improve durability. But the one message of hope is just to remember that many of these vaccine platforms that are being used for SARS-CoV-2 have been used for other pathogens in the past. So we have a lot of durability data from those vaccine platforms that tell us, in the context of other pathogens, some of those vaccine-induced immune responses last a really long time. So I think that we can use that information to, calm the worry, and to basically have some confidence that they will last longer than natural infection may last. But the data will come out over time. And the only thing I have to basically say is the data, and we have to wait till it comes so we can draw conclusions. And we should not assume necessarily that what happens in infection will happen with vaccination.
Thank you. The next question is, 35 years later, why do we still not have a vaccine against HIV?
Oh, that's dear. That's a concept that's very dear to my heart. So I started off as an HIV researcher, and I still do a whole lot of HIV research. Okay, so there are viruses that are really tricky, right? All viruses learn how to evade the immune system. We co-evolve with them, and they essentially know how to subvert, and they know how to propagate. HIV is incredibly mutable. And it is also a virus that integrates itself into the human genome. That is not the case for flu. That is not the case for coronaviruses. These viruses can subvert, they can cause infection, but they can also be cleared. HIV is different. It essentially mutates with every copy of the virus. There's at least one new mutation in its genome. So it can escape all the education process that we throw at it. So imagine you went to math class and someone taught you how to do addition. And the next day they came in and said, oh, no, that's wrong. Do it like this. And the next day they said, no. It's like actually like this. So every single time we try to educate the immune system to know how to fight HIV, it changes because it mutates so rapidly. So the biggest problem that we have with HIV is learning how do you essentially teach the immune system to deal with almost an infinite amount of diversity. It's a problem that is really difficult to understand. And the way we've begun to think about it is by having immunologists like myself start to partner with mathematicians at MIT just across the street to start thinking about how we can basically rig the system. How can we identify components of the virus that may not be sequence-based, but maybe structure-based, to teach the immune system to catch the virus in places where it cannot mutate? And so these are these next generation vaccines that we're trying to develop that are not solely inspired the way Koch and Pasteur and Jenner did it by just, here's a chunk of the pathogen that might be important, but really thinking through little itty bitty parts of the pathogen that we might be able to utilize to subvert the immune system and give us the best chance of hitting these really tricky viruses like HIV.
We have time for at least probably one more, maybe two more, one more, I think. We've heard a lot in the political arena about the concern over a rushed vaccine and what that could be or feel or mean. We have a question. I'm worried that a vaccine might get pushed too early. This is from a student. Is there a chance that that could happen?
Yeah, so this is a really important point. So what I really wanted to emphasize with the timeline, and the reason I put that in there is I think people need to understand this. We are not cutting any corners, right? We are still doing all of our due diligence to make sure that we are making sure these vaccines are safe, making sure these vaccines are effective, and making sure that this is going into the right populations. There will still be a ton of development that's going to happen once the vaccines might get their emergency use authorization in 2021. What that means is that they will be able to be used probably in first responders, right? That's going to be the first population. These are adults where we know we have safety data, but we're still going to have to test it then in the elderly, in kids, in pregnant women. We're still going to have to test for safety also in people who have other kinds of comorbidities. And what I mean by comorbidities is people who are immune compromised or who may not have the most effective immune systems. We still have to do safety testing in all of those individuals. So I have to say that, as much as that this pipeline or development timeline has been politicized, the important thing to remember is that there are incredibly responsible people at the heads of these companies and at the head of these agencies that are not willing to compromise on safety. They are not willing to put anything into someone's arm that could compromise the whole development of vaccines. Because as I showed at the beginning, vaccines are one of our most effective public health intervention tools, and we cannot compromise public trust and process to basically make people happy. It's got to be safe and it's got to be effective.
Dr. Alter, thank you so much. I think that's all we have time for because everyone has to get on to their next class. But Mr. Brennan, do you want to say anything before we leave?
Well, I just want to echo your thanks to Dr. Alter. You not only armed us with incredible information about vaccinology, but more important, you gave us hope, which all of us need right now. And we're very grateful for that. We hope that we'll see you again. at some point in the near future, and that it will be around the time when there are great breakthroughs that you and your various teams are responsible for. That would be a wonderful thing to celebrate. In the meantime, boys, on we go to class, but I hope that you'll remind your parents that we have a mini schedule night tonight for classes 6, 5, and 4. That begins at 6:30. And we'll have a similar opportunity next Tuesday for classes 1, 2, and 3. Please remind your parents that this is a great opportunity for them to hear from your teachers, to see them, obviously virtually, but to also learn something about what all of you are benefiting from in going through each day. Thanks very much. Have a great day.